Good morning or afternoon or whenever it is that you are watching this. In continuation with our probability adventure, we are going to start tying multiple events together and calculate their probabilities, unlike what we did at the end of last week, which was just simple events where we have one event, we have to calculate its probability, what we algebraically called P of E. Now we're going to start calculating multiple events. And let's start nice and simple here. Okay. And the example problem to kind of get us thinking is when flipping a quarter and a dime, what is the probability of landing on heads on the quarter and also tails on the dime? So this is the example. I want you to think about it. So go ahead and pause the video if I didn't say that and see if you can figure out what is the probability of heads coming up on the quarter and also heads on the dime. Okay, so this is an example of a compound event where we're asking for the probability of multiple things happening. All right, and there's two things that you have to be aware of when you're considering multiple events happening. Actually, they can become very complex, but we're going to start simple. And you have to analyze, are these two events independent events or are they dependent events? We'll talk a little bit more about what these mean. But the two quarters, spoiler alert, sorry, the two coins, I should say, one's a quarter, one's a dime, are independent events, all right? So the first thing that we're going to do is just do what we did last week. Let's make a tree diagram, all right? So the quarter can first and foremost land on heads or tails, and this should look relatively familiar to you. This top row is representing the quarter. It can land on heads or tails, and from there, let's say the quarter lands first and it's spinning around and it lands on heads, well then the dime can actually stop spinning around and land on heads, or it could also land on tails. If the quarter had landed on tails first, then the dime could land on heads and the dime could land on tails as well, right? So obviously you're seeing that there are four events. All right, so the problem is when flipping the quarter and the dime, what is the probability of landing on heads on the quarter and also tails on the dime? So that is one branch of our tree diagram out of four. So we should say that the probability of this, there is one favorable event that meets the constraint, and there are four total events, right? There are four branches of the tree. So you could say that there's a 1 in 4 or 25% chance, okay? Or a 25% chance. But the other way to conceptualize and to calculate the total probability of multiple events happening is to multiply the probabilities for each event together, and the product will be their compound probability. Okay, so the probability of landing heads on a quarter. So stop and think about that. What is the probability that the quarter itself, just the quarter, lands on heads? Hopefully you're thinking, okay, there is one outcome that is favorable out of two. And the same thing is the case for the dime. So if there is one favorable event out of two for the quarter, and I'm multiplying that times the probability of landing on heads on dime, which is also 1/2 times 1/2. Now we have to think about our fraction multiplication, okay, which is we multiply the tops, the numerators, 1 times 1, the product is 1, and 2 times 2, the product is 4. And we see that the probability that we got in the last problem, where I actually drew out the entire sample space, is the same as I got here. 25% or 1 in 4. Okay? But which is the better method for this? When pulling a card from a deck, if you notice there are 52 cards in the deck, and rolling a die, a number cube that has 6 sides, what is the probability of pulling the ace of spades and rolling the number 1 on the die? Okay, when this compound event happens. Okay, so would you rather make a tree diagram for this event, or would you rather just figure out the product of the two events? And hopefully you're thinking, yeah, nah, a tree diagram, that's going to take way too much time. Not that it would be impossible, but you would have 312 different outcomes here. You would have 52 times 6 different outcomes. Nah, we don't have enough time in our day. We're going to go, there is one ace of spades, that is a very specific card, out of the 52 in the deck. Okay, and we're going to multiply that times there is 1 1 on the die, 1/6, and we could go ahead and multiply those two probabilities together. 1 in, what did I say, 312. Correct? So we'd say that the probability of ace of spades, let me draw a spade, and landing on 1 on the die is equal to 1 over 52 times 1 in 6, which is 1 in 312. These are examples of independent events, right? The card was not affected in any way, shape, or form by what happened on the die, and vice versa. What happened on the die was not affected by what happened on the card. So you would say that these two events are independent of one another. Okay? So let's think about these two problems. What is the probability of a mother having 3 children, all of whom are girls? There was a very similar problem on the most recent homework, right? So make a tree diagram if you need to, but let's think about, okay, what is the first event happening? What is the second event happening? And what is the third event happening? Let me pause the video and see if you can come up with the same. Okay, and I took the time to not only lay out the calculation, but also make a little tree diagram, which might be a little tough to see. But if you notice, if the mother is expecting a child, and the probability of that child being a girl is 1 in 2 possibilities. So it's 1/2 for the first girls to happen, and then is the second child affected in any way by what happened the first time? And the answer is no, of course. It's still a 50-50 scenario, a 1 in 2 for the second child to be a girl, and it's also a 1 in 2 scenario for the third child to be a girl. So if we multiply these 3 fractions, these 3 ratios together, we'll get 1 times 1 times 1 is 1, and then 2 times 2 times 2 is 8 on the bottom, and it is a 1 in 8 chance, or 12.5% chance, that if you have 3 children, they're all girls, right? Mrs. Cummings' family was like that. And you see the tree diagram. See, there's 8 stems. 1, 2, 3, 4, 5, 6, 7, 8, and only one of them is favorable. Only one of them has the constraint that we're looking for. Girl, girl, girl. Okay? But even if they have percentages associated with them, the same scenario is still the case in how we are going to calculate. So let's say that there was a 70% chance of snow and a 65% chance of UNC winning on the weekend. I'm not sure what sport this is. It doesn't really matter. Okay? What is the probability that it snows and UNC wins? Go ahead and let's multiply those 2 ratios together. Okay, so with the calculator here, 70% times 65% came out to 45.5% chance. And you might be noticing something here. The more events that I am tying together as one event, called a compound event, the smaller the probability is getting. So it seemed fairly likely that it was going to snow on whatever weekend this was, and it seemed also fairly likely that UNC was the favorite in this game, whatever game that was, but the probability of them both winning is actually slightly less than half, slightly what we would call unlikely. Interesting. All right, might have something to do with, as you're multiplying numbers that are smaller than 1, the numbers keep getting smaller and smaller. Okay, so independent events, as we have discussed in every example thus far, independent events and their probabilities do not affect each other because either they are completely separate, like a coin and a die, the event is reset in some way, okay, or something is replaced. Okay, so if I'm doing flashcards, sight words flashcards with my daughter, if I put the word back in the deck, I might shuffle them up and I still get that same word again. Okay, that would not be the case if I took the card out of the deck, and we'll talk about that in a second. Okay, so we find the probability by multiplying the probabilities for each individual event like we had in the last. So rolling 2 dice, these are independent events. The 2 dice do not care about each other in any way, right? The outcome on the first does not affect the outcome on the second. Spinning a spinner 3 times. The spinner don't care. The spinner does not care what happened the first time, second time, third time, right? If you got 1 3 times in a row, you are just still as equally likely to get the number 1, whatever that might be, Okay, and if I'm pulling names from a hat, imagine every person's name in the hat from the class, and I pull a name out, but then I put it back in. The game has been reset, and everyone still has equal probabilities, equal chances that they had the first time. Those are called independent events. Okay, so let's calculate the independent probability. This bag contains 3 red marbles, 5 white marbles, and 4 blue marbles. 2 marbles are drawn randomly with replacement, meaning that they get put back. What's the probability of a white one first and then a red one? Go ahead, try this problem on your own. Okay, let's check it. So the probability first, when the bag has nothing has been touched, of getting a white one pulled out should be 5. There are 5 of these white ones out of a total of 12. So the probability means that we have 5 white marbles, 5 favorable outcomes out of 12. So I pull one out, and then I put it back in, I shake it back up. Now the probability of getting a red one is there's still a denominator of 12. Now there are 12 marbles back in the bag, and there are 3 favorable outcomes for the red one. Okay, so the compounded probability is going to be these 2 probabilities multiplied together. Okay, let's see if I can do a little cross canceling so we don't have to go to the calculator. Oh no, I don't want text pen. That's definitely not what I want. It's been a while since I used this program. Here we go. All right, let's do a little cross canceling here. I'm just going to factor out a 3 and making this 5 times 1 in my numerator is 5, and 4 times 12 in my denominator is 48. It has a 5 in 48 chance of that compound event happening. These are independent events, right? Something was reset, okay? But that's different from this thing called dependent events, right? With dependent events, the first event has changes the probability of the second because the game is not reset, or the event has changed in some way, or something is not replaced. These can be 2 or more compounded events. You will still need to find the probability by multiplying them together, right? Multiplying each individual's probability together. So dependent events could be pulling the name from the hat and not putting it back in, right? So if I had a student and I pulled her name out of the hat and I did not put it back in, every single other student's chances of being pulled have increased, and there is a 0% chance that that student is being pulled again. Okay, Ravenscroft beating Cary Academy in the semifinals, and then Ravenscroft beating NRCA in the finals. Okay, these are dependent events because the second event cannot even exist, cannot even happen if the first event doesn't actually occur. Okay. And then being dealt a queen and then being dealt another queen from a deck without putting it back, right? So if there's no replacement that happens, the deck has changed, right? The ratio of the second card has changed in some way, okay? The more queens that get dealt out of a deck of cards, meaning it is less likely, or at least different chances for the second queen to be pulled, I should say, okay? It depends on the game and how many people are at the table and other kinds of factors. But anyway, I digress. You are pulling 2 cards from a deck without putting them back. What is the probability of a red 4 followed by a black ace? This is a very random specific event, but these are dependent events because if I pull out a red 4 from the deck of cards, that is, let's say this one gets pulled. That is the 4 of hearts. My pen is not working. This is not very satisfying. Let's go to one of these pens. Yay. Okay. Let's say that one gets pulled out. That is how many red 4s are there in a deck of cards? Well, there's obviously 2 of them out of a total deck of 52. Okay. But here's what I want to ask you. Okay. After that card got pulled out, what is the probability now of pulling out one of these black aces? That is either the ace of clubs or the ace of spades. Well, there are definitely 2 of those. There are 2 favorable events. There are 2 favorable events. But now I have a deck that only has 51 cards in it. We need to remember to subtract out 1 from the sample space. because there is one less card because I took out that 4 of hearts in that particular case. Okay, so you're going to have to go ahead and multiply these two numbers in the calculator. We can do a little cross canceling. 1 and that'll become 26. Ooh, and I could do some more cross canceling. That'll become 1 and 13. And then my compound probability, you can just do this with the TI-34 calculator. 1 times 1 is 1 on the top, and then I have to do 13 times 51. 13 times 51. 13 times 51. It's going to be 663. So that very specific event is a 1 in 663 chance of happening. Let's go pick up the pace here. You are pulling 2 cards from a deck of 52 without putting them back, without replacement. Okay, what is the probability of getting an ace followed by another ace? Okay, well, there are 4 aces in the deck of 52. You are not being assessed on the deck of cards, by the way. If I have a deck of cards problem, you're going to just get a deck of cards to just fully look at. Okay, 4 out of 52, which if I wanted to make my life easier, that is 1 in every 13 cards, and I'll do that in a second. But let's just make it as simple as possible. There are 4 aces in 52. Now let's say the ace of clubs got pulled. What is the likelihood of the next event happening? Well, now there are 3 cards. There are 3 aces left in a deck that now has 51. We're going to have to subtract 1 from the numerator and subtract 1 from the denominator because there's 3 aces left in a deck that now has 51 total cards. Okay? Actually, yeah, this can get simplified a lot because different color. This is 1 in 17. No, this is 1 in 13, excuse me. And this fraction is 1 in 17. I'm just reducing common factors. Now my numerators are 1 times 1, which is 1, and my denominators are 13 times 17, which is 221. And that is the compound dependent probability. Okay? Do this one on your own. A bag contains 3 red marbles, 5 white marbles, and 4 blue marbles looking a lot like that. This time, 2 marbles are chosen without putting the first one back. What's the probability of getting a red first, it doesn't get put back, and then a blue one? Pause the video, let's get the same answer. All right, sweet, let's check it. The probability of the red marble, there are 3 red marbles in a bag of marbles that has 12 in it. Okay, so we pull one of those red ones out. There was 3 out of 12. The first event has happened. Now, what is the likelihood of the second event happening? That red marble that I just took out does not go back in. That red marble does not go back in. What is the likelihood of a blue marble being pulled? Well, now there is 1, 2, 3, 4 blue marbles in a sample space of 11, right? So there were 4 out of 11 that had to happen there because of the dependent probability. You guys can just type these 2 fractions into the calculator and then hit equals answer and then simplify as necessary, or you can go ahead in this one, do it by hand and cross cancel. This is going to work out great, I can see already, because if I just reduce this fraction, now I cross cancel these factors of 4s. I only have 1 times 1 on the top, which is 1 as a numerator, and then 1 times 11 on the bottom. This is a 1 in 11 chance of this event happening. Red then blue is a 1 in 11 chance. Okay, and hopefully that is enough to get you going on independent and dependent events. Okay, on your homework assignment on the practice sheet, you have to first of all say whether the events are independent and or dependent, and then you have to calculate the compounded probability. Let me know if you have any questions, and I'll be here to answer them. See you guys.